All right, students, I got a question on a circuit here, number 3. Let's read it together. It says an automobile battery has an EMF of 12.6 volts and an internal resistance of 0.08. All right, so I'm going to go 12.6 for the EMF, and I'm going to put in little internal resistance, 0.08 ohms. And I kind of like to always put kind of a dotted line around these to kind of show that this is one physical device. This is the battery. This is, the chemical reaction. It said car battery or automobile battery, so I'm sure this is a lead and acid reaction here. And then this is kind of the pieces that make it up, mostly sulfuric acid, and trying to move all those charges through the sulfuric acid and through the lead and the lead oxide. So that's our battery, if you will. And then it says it is hooked up to some headlights, which they say the two of them together are equivalent to 5 ohms. So we got both lights on. So it's probably like 2 in parallel, a 10 and a 10, because if you take a 10 and a 10 in parallel, the equivalent is a 5. But we don't need to know that. We just know that the headlights are connected there. And then it says, what is the potential difference across the headlight bulbs, A, when they are the only load? All right, well, if we do a Kirchhoff's loop here, I suppose it doesn't matter where we start, so I'll start in the upper left corner, and I'll say that the current goes around in a clockwise direction. So when I get to here, this would be a minus 5 times the current. And when I get to here, I still would be going with the current, so it would be a minus, and it would be 0.08 I. And then it would be a plus 12.6, getting back where you started. So this is the loop rule, the easiest one to do, because it's just one loop. And then we can solve for the current here. So 12.6 equals 5.08. When I put those together and move them over here, make them positive, is I. And that gives me a current of 12.6 divided by 5.08. And so the current is 2.480 amps. Now, the question wasn't really so much the current, but the voltage on the headlights. And again, note that because the current's got a flow, there'd be a loss of voltage. So if you just took a voltmeter to the terminals, what we call the terminal voltage, it should lose a little here. Now, not much, but a little bit. And so this 12.6 is going to go down a little bit because of the amount of current through here. In fact, we could calculate how much it's lost and just subtract that from the 12.6. Or we could calculate the voltage straight across the light bulbs. And I think I'll do that one. So if I just look at the light bulbs, I know that the current is 2.48 amps. And the resistance is 5 ohms. And so I'll just take that current and multiply by 5, and it looks like we've got a 12.4 volts. So the terminal voltage would be 12.4 volts. Not too much below the 12.6. In fact, you can then predict that voltage drop here should be the 0.2. And what we'll see, voltage equals 2IR. So if I take the current that goes through this battery and then the resistance of that internal resistance, that should account for the 0.2. There it is, drop. Okay. So like I said, we could have done the drop and just subtracted it off, and then it would, give I think a better picture of what we mean by a drop in a terminal voltage. But this was just so easy. Calculate the actual voltage across them by just taking the current times the resistance. Now, it looks like the harder part of this is B here. It says, what about when you're trying to do a starter motor that requires an additional 35 amps? Okay, so it would look something like this. Here's the battery again, 12.6 from the EMF. Here's a 0.08. The big thing to remember, though, is now not only are we running the headlights, but we're running a starter motor, which they don't tell us the resistance. So I'm just going to put R. And so we got two things in parallel running at the same time. And that means we're going to need a lot more currents because they said the current coming through here is 35 amps. Now, if, and this is a big if the current stayed the same in the light bulbs, 2.5 amps roughly, then we're talking about 37 amps that have to come out here. And see, that's why there would be then a bigger loss, because it wouldn't be just simply 2.5 times 0.08. Now it's going to be way up there at something like 37.5. Okay? But I would even argue then that it's going to be even more complicated, because it's not just in addition to that, there's going to be a change in the terminal voltage, which is going to reduce the current in the headlights, which is why if you've ever seen, a car start, the headlights will dim down a little bit, or starting a dryer in your garage. I often see this. I got this one little tiny light, and you push on the button to start the dryer, and then the light dims there a little bit, and that's a little bit of drop in current because of the large current needed to start the load. And then once it starts, then it's not much current, so then the light goes back up. So it's just a momentary flash. Now, starting the car, it would only go dim while you're actually starting it, and then you let up on it. Anyways, but now we have two loops here, and we have a node. And if we then say the current coming out of the battery is I1, and it splits off and goes to the headlights of I2, but also goes to the starter motor of I3, we can see right here at this node, we'd have current coming in, which is I1, would have to equal to I2 and I3. So there is what I guess I would call the first equation. Current in equals current out. Okay, and that's conservation of charge. Now, we actually know this current number 3, so maybe I'll just cross that out and put 35. Okay, so we have just 2 unknowns. Now, if we do a loop here, and if I do the left loop, I would get something that I guess looks like this. Starting over here in the upper left-hand corner, I'd go with current number 2, so there's a minus 5I2. Circles around, coming back with the current. See, that's what this is saying. So with the current, so another minus 0.08I1 plus 12.6 equals 0 to finish off. And that then would be my second equation. And is enough to actually solve this, because they gave me one of the currents. A lot of problems give you the resistance, not the current, and so you have the 3 unknowns. And we could actually treat this as 3 unknowns. Maybe I'll write it out. If we did this right loop, maybe starting here and going clockwise, here we'd go with the current, so it would be minus R times the current of 35. And then here we'd go against the current, so it would be a plus, and then it would be a 5I2, and that would equal 0, finishing up that loop. And, excuse me, if you kind of look at the math here, we technically have our 3 equations, 3 unknowns. Instead of the 3 unknowns typically being the 3 different unknown currents, here we have one current but don't know the resistance. So we have the unknown of I1, I2, and resistance R. However, we could probably solve this one by not solving for R, but solving for just current 1 and current 2. So if we were just to kind of take a subset here, we get kind of lucky. These two equations have just two unknowns. And so instead of me getting my calculator out and doing a little matrix, I'll do this one by hand. Let me start with this second row here. This would be minus 5. And maybe I'll just leave this as I2 right here. Minus 0.08. And in place of I1, I'm going to put the first equation, which says I2 plus 35. Okay, so that's how I'd get rid of number 1 and, of course, change it into number 2. And then plus 12.6 equals 0. So if we kind of do the distributive here on this I2, we would get a negative 5.08 I2. And then also in this distributive property here, we would have this 0.08 times the 35. And so that's a 2.8, and it's got a negative with it. So when I put it together with the 12.6 and then subtract the last answer, that is then a plus 9.8 equals 0. And then solving this for I2, so kind of imagine this moving to the other side, that would make that a positive. So I've got 9.8 divided by 5.08, and so current number 2 is now 1.93 amps. And that's really what I want to get. Remember, before we were getting a current of 2.48 amps through the headlights. Now it has dropped down a little bit. And your eyes are pretty sensitive, so it's not that much drop in current. You'd easily notice in the brightness of the lights, and you'd go, oh yeah, all right. Must have been, having a demand on that battery. I was stressing that battery. In fact, you can see that. So now to get the terminal voltage, I'll just do what I did before. Now that I got the current through the battery, I'll just multiply by the resistance. So let me take that current and multiply by a resistance of 5, and we're looking at 9.64. And hopefully that makes sense. And now the terminal voltage has dropped. And of course now the lights are kind of struggling. That's kind of a low voltage to run your light, and for that matter your starter motor. So it's starting to, drop. Probably still enough to start your car, but it's, like I said, taking a lot of strain on the battery here. Of course, it's a pretty high internal resistance for a good lead-acid battery, so I'd say this is not that great of a battery. So it's not bad. It probably still starts your car, but probably within the next year you're going to need a new battery. Okay, so here is the voltage. Now, just as my own curiosity, we could do the same thing we did before. We could look at the drop here. And so if I look at the drop, the resistance on the internal resistor is 0.08, and the current going through this internal resistor would actually be this current from I2, which is 1.93, plus the 35 that's going through the starter motor, because see, the starter motor wraps around and joins up with it, and so the total current is the 2. That's why the terminal voltage is so much less now. So if I take that 1.93 and add it to the 35, that's the current. And if I multiply it by an internal resistance of 0.08, we're looking at a 2.95 for a voltage drop. So that's how much we lose. That's why if we, again, take our voltmeter over the terminals, we would then not get the 12.6, but the 12.6 minus the voltage loss, trying to get the current out of the battery. And of course that is than the 9.64 that we got up here. And so again, maybe it's easier to see when we see it as a drop and internal resistor taking it away from the terminal, or taking it away from the EMF, so the terminal voltage is less. That's the voltage on the headlights, and for that matter, the voltage on the starter motor. All right, hope that helps.